to see how we can deal with continuous charge distributions and get the electric field at a point in space due to a continuous charge distribution. So first, before we do that, let's review what we discussed before about point charges. So if you have several point charges in space, Q1, Q2, Q3, and so on, how would you get the electric field at point P? We did that by first getting the electric field due to Q1, and we assumed in that case that all the other charges don't exist except Q1, and we got one vector. And then we got the electric field due to Q2, again assuming that all other charges don't exist. And then we got the electric field due to Q3 and assumed the other charges don't exist. And what did we do with those three vectors? We added them as vectors. And in that case, we get the resultant electric field at point P, which is this red vector that represents the total electric field at point P due to all the charges that exist in space. This is the only thing we know how to do. We only know how to get the electric field due to point charges. So how would we deal with an object like this if it's a contour of charge, if charge is distributed everywhere on a line of charge, contour? How would we get the electric field at point P? The only way we can do this is if we cut it up into small parts. And we have to cut it up into small parts such that the small parts tend to zero size, because we only know how to get the electric field due to point charges. So if these elements of length remain finite, large, then the electric field, we can't get the electric field due to those large pieces of charge. We have to cut it up into smaller and smaller parts until the number of elements goes to infinity or the size of each element goes to zero. We could get the electric field due to delta Q1, and the electric field due to any charge is Ke times the charge divided by the distance between the charge and the point squared times a unit vector that points from the element of charge to the point, r hat 1p. That would be the electric field due to charge 1 in the limit when this size of this element of charge is 0. We would get the electric field due to the second element of charge, and it's the same idea exactly, but instead of delta Q1 you have delta Q2, instead of R1p you have R2p, instead of R hat 1p you have R hat 2p. And this unit vector is not necessarily the same as this one, because the element of the unit vector points from the element of length to the point. This is what the electric field would be due to the ith element of charge. So you have delta Qi, you have Rip, R hat Ip, and this gives you delta Ei, the electric field due to the ith element of charge. It's the same thing exactly. So now, how would you get the electric field due to all these elements? Clearly, you have to add them. You have to add them as vectors. So this is an expression for the summation. You're adding the electric field due to each of the element of areas, and then you have to take the limit when the size of the elements of length tends to 0. This limit of sums can be written as an integral. Formally, it can be written as integration of Ke dq over r squared r hat. There's the r squared, there's the dq, and there's the r hat, the unit vector. And remember that this r hat unit vector is not constant. It changes from different elements, from point to point on the contour. This r hat changes. R also changes. R is the distance between the point and the element of length on the contour. And this distance changes, so it's a variable also. So in general, this problem is quite difficult to do. We're going to only solve problems that are relatively easy to do in this course. Now you can replace dq when you have a line charge by lambda dl, and then formally this would be a way to get the electric field due to this contour of charge. What would you do if you had a surface area, an area full of charge, or a charge distributed over an area? How would you get the electric field at point P? Idea. You have to cut up your area into small elements of area, and you have to take the limit when the element of area goes to 0, because the only thing we know how to do is to get the electric field due to a point charge. So you would write exactly the same formula we got for the line charge, but now for the area. This is the electric field due to the ith element of area, and you have to then add the electric field due to all the elements of area, and this is the summation, and you take the limit when the size of the element of area goes to 0. That would be the exact electric field, and this limit of sums can be written as an integral, same exact expression as before, integration of k dq over r squared r hat, but in this case dq can be replaced by sigma dA because we're integrating over an area. In general, this integration is not easy to do, and so we're only going to deal with simple problems that can be solved in an easy way. Okay, what would the situation be for a volume charge distribution? How would you get the electric field at point P when you have charge distributed in this volume, any kind of volume? Well, it's the same idea. You cut up your volume into small elements of volume, and you take the limit when the size of the element of volume goes to 0, because we only know how to get the electric field due to point charges. This is the electric field due to a point charge. You sum over all the elements of volume in the limit when the volume size goes to 0. And this can be written as an integral, integration of ke dq r hat over r squared, exactly the same form as we had for all the other cases. But in this case, dq can be replaced by rho dv.